talking about polar molecule, guys. So far, we talked about one bond, polarity of a bond. What if we are dealing with a molecule which has more than one polar bond? So in this case, in water, can I say, I think electronegativity of hydrogen was 2.1, electronegativity of oxygen is 3.5. The difference of electronegativity, is it 1.4? That makes this bond polar. Which direction electrons are being pulled toward more electronegative atom, which is oxygen. Also, the other hydrogen-oxygen bond is polar for the same reason. There is a difference of electronegativity. So electrons are also being pulled from hydrogen to oxygen. Could I say lone pair are electrical charge? Lone pair have electrical charge. Can I say there is some negative charge because of these? There is some negative charge on oxygen because of oxygen pulling electron away from hydrogen. So if I'm going to look at the net polarity of water, can I say electrons are being pulled from the bottom of molecule where the two hydrogen are toward the top of the molecule where oxygen is. So that's the general polarity of all the bonds and lone pair. So we call this molecular polarity. So can I say molecular polarity is result of some adding all polarity of bonds together. Another word, I can look at water molecule where oxygen is at top with negative charge and the two hydrogens on the bottom with positive charge. So water looks like a polar molecule. One end is negative, one end is positive. So water molecule is polar. It's different from saying that oxygen-hydrogen bond is polar. So polarity of the molecule is the net polarity. When you're adding all the electron pool, electron pushed together, the net result. So I'm going to look at this other molecule, chloromethane. So if I say, guys, is the bond between carbon and hydrogen polar or not? You say 2.1 for hydrogen and 2.5 for carbon. The difference is 0.4. It doesn't matter positive or negative. And 0.4 difference of electronegativity is not large enough to make a bond polar. Remember, we said a minimum of 0.5 is needed. So can I say carbon-hydrogen bonds are nonpolar? Can I say that? So we have three nonpolar bonds, this one, this one, this one. What about the bond between carbon and chlorine? Electronegativity of carbon, 2.5. Electronegativity of chlorine, 3.0. The difference is 0.5, and 0.5 is minimum you need to make a bond polar. That means between carbon and chlorine, which has larger electronegativity by 0.5, is pulling electron away from carbon. So the net polarity of molecule, which is the result of considering all these four bonds, is pull of electrons of carbon toward chlorine, and that's what you see. Chlorine end has more electron cloud with more negative charge. The hydrogen ends are blue, is suffering from shortage of electron cloud positive. So if I want to show direction of polarity, I always start from positive. I draw an arrow toward the negative, just like this. So this is showing that chloromethane, this molecule has positive end and negative end. So overall, this molecule is polar. All right. Is carbon dioxide molecule polar or not? Well, carbon 2.5, oxygen 3.5. The difference is 0.5. Yes. Carbon-oxygen bond is polar. Which direction electrons are pulled toward more electronegative atom, which is oxygen. So you have electron pull toward oxygen. How about the other side? Other side, the same thing, electron pull toward oxygen. Can I say these two equal pull to opposite side, they cancel each other? So you have zero net polarity. So do you see why we study geometry? We know geometry of carbon dioxide is linear. We also know that if we have let's say a large box, you're pulling in one direction, somebody is pulling in opposite direction, equal and opposite forces cancel each other, so there is no movement. So carbon dioxide, because of that reason, is nonpolar. That's why carbon dioxide is gas at room temperature, it's nonpolar. Water is liquid at room temperature, is polar. When molecules are polar, they attract each other from opposite ends. The forces between molecules can keep them from flying away and becoming gas. In gas molecules, there is minimum interaction. In water, there is a lot of interaction. You have to heat water to evaporate. That means there is a strong interaction between opposite end of water, which keeps water in liquid form. You want to evaporate water, you have to add a lot of heat to break the bonds between opposite end of water molecule. So zero net polarity in this case, you have a pole, I'm sorry, no. These are all chlorine. So is each one of these bonds polar or not? Yes. The difference of electronegativity between carbon and chlorine is 0.5. But in this bond is polar, electrons are being pulled toward chlorine, toward chlorine, toward chlorine, and toward chlorine. Now, knowing that this is a tetrahedral structure, if you add all these forces together, you get a net force, which is equal and opposite to the pull toward the top. So the net forces, three of them pulling down, one pulling up, they cancel each other. You may say, why? One pull is canceling three pull because of the angle. It's possible when you take physics and you look at vector sum, you will see that these three pulling electrons toward the bottom is equal to the electron pull toward the top. So net polarity is zero. Okay. So if I want to look at, would a linear water molecule be polar? Suppose water remember we said water is bent based on our prediction. What if water was linear? There would have been pull of electron toward oxygen, pull of electron toward oxygen, equal and opposite pull will cancel each other. This water, if it is linear, is nonpolar. That means water wouldn't have been liquid at room temperature. That means we wouldn't have oceans. And that means we know the life started from oceans. That means you and I would have been evaporated because we are 63% water. That means the difference between this angle, which is 109, and this angle, which is 180, makes life possible or not possible. That's how much geometry of molecule matters. That's why we're studying geometry of molecules. And why is water nonlinear? Because there are two lone pairs, don't forget that. This lone pair is pushing shared electrons between oxygen and hydrogen away from themselves. These are pushing. So there is no way that the two bonds between oxygen and hydrogen can be at 180 degrees. We have 4 different electron pools. These are electron pools pulling electron toward oxygen in these two hydrogen oxygen bond. We said lone pairs have excessive electron cloud at one end and a smaller electron cloud. So overall, lone pairs behave like a tiny electron pool. So if we add all of these together, they do not cancel each other. And as a result, the molecule overall is polar. And we said you can measure the extent of polarity. The extent of polarity is shown by dipole moment. The unit is dBi. The larger, and this is the letter mu, which shows polarity, dipole moment. The unit is dBi. So water has a dipole moment of 1.85 dBi. That means if you are comparing two polar molecules together, you're going to be looking at dipole moment value. The one which has larger dipole moment is going to have larger polarity. So let's practice on the next slide.